All right, so this is going to be example 1. And I want to start with basic examples and kind of work our way up to more complicated examples. The thing that you're going to be disappointed about is that we don't get to actually throw away the stuff from dynamics. Everything in the class tends to have, kind of builds on something we've done before. But using work and energy to solve problems is, in some ways, much easier than what we had to do when it came to Newton's laws. Newton's laws was a framework. It gave you a method to do a problem. The problem I'm about to state can be done using Newton's laws too. So you can always use Newton's laws. It's just that there are easier methods. Now, what I'm not really inclined to do is to do the problem both ways to show you that it's easier to do it one way versus the other. I don't think that you guys need that. I want to talk to you, though, about the similarities for a little bit. Let's say I have a 20 kilogram box that's going to experience a 15 Newton force at an angle of 30 degrees. And for the time being, let's say the surface is frictionless. You pull the box 10 meters across the floor. I'd like to know how fast it's going when it makes it to the 10-meter mark. Now again, this is an example question, so I'm not actually asking you to do it. I want to talk to you about ways that this problem can be done and why you might want to choose one way versus another. First, this problem could clearly be done using Newton's laws. It should be clear that it could. If not, think it through. There's enough information for you to set up net force equals ma. From here, you should be able to tease out the acceleration. And from there, you should be able to do a motion problem. And that should be able to be used to find the velocity. You'd have to start at the free body diagram, put a coordinate system in place, identify the forces and which direction in which they act, which one is set to 0, which one's set to ma, work through to get the acceleration, and then you could get the motion problem after that. However, there is something about this problem that should identify for you that energy would be a faster way to solve this problem. And I'm going to tell you the 3 things that you should look for. First, energy problems tend to be about velocity and displacement. Energy problems tend to be about velocity and displacement. So if your problem is interested in velocity, you should steer yourself more towards using energy than using forces. Remember, I said that force problems are about acceleration and forces. So if you're asked to find an acceleration, you're probably stuck using forces. But they don't actually ever ask what the acceleration is. They ask what the final velocity is. So if your question is about velocity, it's steering you towards energy. Now we're going to find there's other things that are about velocity too, momentum being one of them. So sometimes they'll have to delineate. But what makes this an energy problem and not a momentum problem? They give displacement. So problems that are about velocity and displacement are almost always best done using energy. Yes, ma'am?
So both velocity and displacement?
Yeah. What you will notice too, actually you might not notice it, it's an omission. We've never mentioned how long any of this takes. I've never brought up time at all. Energy problems are not good for dealing with how long something takes, and therefore are not well suited for problems that ask how long does it take to get there, or how long will it take to get there, or if they give you it took 7 seconds, probably not energy. So when you're trying to, because remember, your exam's not going to say, this is the force problem, and this is the energy problem. So far, you've been kind of in a position where I give you a question, and you know it's a force problem because that's what the test title is. But you understand it's not going to be like that forever. You have to delineate. So look for changes in velocity that accompany displacements. Those are almost always best done using energy. Yes, sir?
You said for force, it's an acceleration and...
A force, solving for the size of a force.
Got it. Thank you.
So how would we approach a problem like this? The fact that I see that they're asking for how fast it's going, that identifies to me change in kinetic energy. You hear anything about velocity, I'm thinking change in kinetic energy. But also, they did something very specific that makes this a work problem. Force and an angle. They gave us the size of the force and the angle compared with displacement. Those are two huge alarm bells that work is probably the best way to go. Now, I know we've done problems where they give a force and they give an angle, but very seldom did they give force, angle, and a displacement. That didn't happen very often in force problems. They weren't as concerned about that. So, to me, this feels like a problem where we could deal with work, and then from there, use it to deal with the change in kinetic energy. So, now that I've identified what I think the best route is for this problem, let's start with the work portion. Work is defined as the force times the displacement times the cosine of the angle between. I don't have to draw a free body diagram. If I know the angle is between the force and the displacement, I'm going to skip the free body diagram and just calculate how much work this force does. And we know from prior examples that, there's other forces that potentially could be doing work at the same time, but it's frictionless, and any other force that would be acting on the box would be up or down. Those forces can't do work. They're not in the direction of motion. So right now, I am confident that this is the only work being done on the box. Now, if you're in your notes, you want to know why I just said that paragraph, I would say in your notes, a good thing to do is to ask yourself what other forces could potentially be doing work. Are there any other forces in the direction of motion? You really should think about that before you decide on a course of action. Now at this point though, 15 times 10 times the cosine of 30 degrees. Pretty straightforward. I'm not going to do this in my head. I think you guys can rifle that out. So go ahead and give me a value here. What's that?
23.1.
It's not 23. Sorry. Is your calculator in degrees?
29.9.
That sounds right. So I'm going to go with 130 if that's all right. This will be joules because it's newtons times meters. This represents the work done by the applied force. Now, this part's hard. This is where the details come in, and here's where if I'm trying to trick you, or if I'm trying to see if you really understand, which to me are the same thing, I would try to see if you really are thinking it through. Is this the net work being done? You need to ask yourself if it is or not. And it comes down to net work is the total work done on the object. So are there any other forces that are doing work on this object? Any other forces that are within the direction of motion or aligned with the direction of motion? If the answer is no, then it's very likely this is going to equal the change in kinetic energy. Very likely. So if I believe that I'm in that position to say that it's equal to change in kinetic energy, I can say my 130 joules equals 1/2 mv final squared minus 1/2 mv initial squared. If we believe this is the net work done on the box, then that's all that we have to do to figure out how fast the box is going. Now, this is just, plug and chug kind of stuff. I'm not particularly interested. You guys should show that the final velocity is equal to the square root of 13. You guys get that? Now, here are some things I want you to think about. If your problem is like this, if you're just asking for a velocity, these problems are pretty straightforward. Set the work equal to the change in kinetic energy. It's that straightforward, it's that easy. And although this is not the easiest form of these problems, we're gonna be doing some stuff in a couple days that's even easier than this. The work energy problems are about following the flow of energy. I did work on the box, therefore the box energy changed. It went from having no kinetic energy to having 130 joules of kinetic energy. Since there was nothing else to take that energy away, the only place the energy can go is kinetic energy. I want to say this very clearly. Energy always goes someplace. You have to account for all energy in a problem. We haven't talked about this word yet, but energy is conserved. This is going to come up a couple times this week. So when you do work on an object, when you give an object energy, you have to account for all the energy given to the object. So I gave the object 130 joules. It's your responsibility to figure out where that energy went. If nothing takes the energy away, the energy stays with the object. I'm going to say that very clearly. If nothing takes the energy away, the energy stays with the object, which means there's only like 2 or 3 places the energy can go. This is example 1, our first introduction. Pretty easy, I think. Any question about this one? Can I increase the level of difficulty? No. Yes, ma'am.
Why do we plug in 130 joules to that formula?
Here?
Yeah.
This was the amount of work that I did on the box. So that became the amount of energy that went into kinetic energy.
Oh.
If I ask myself, is this the net work being done on the box?
Yeah.
And if it is, I can set it equal to the change in kinetic energy, and that's what this is.
Okay.
So this next thing I want to do is kind of something that you would have you would miss if you weren't, well, a physics teacher. So let me show you that you've already been doing this. What if we had to do this problem the other way? Okay? If we had to do the problem the other way, meaning we were going to find the net force on it, and then from there use the acceleration to figure out how fast it's going. I want you to look at the variables we would have had. We would have used the acceleration, and the acceleration would be paired with the initial velocity, the final velocity, and the displacement. Do you remember the relationship that has these 4 things in it? Like from your sets of motion equations? This is actually on the equation sheet, I believe, too. But if you look for it, it's the one that doesn't have time in it. And it's V final squared minus V initial squared equals 2A delta x. Look familiar? Bear with me. I know you guys hate it when I do a bunch of algebra, but let me do a bunch of algebra, all right? I'm going to multiply both sides of this equation by m, the mass of the object. okay? Just multiplied everything by m. I'm going to divide both sides by 2. I'm going to notice that net force equals ma. Do you see what I'm trying to show you? This is the work done by a net force. This is net work. This is clearly the change in kinetic energy. You've actually had the work energy theorem as a motion equation the whole time. And it's the go-to here for what we do when it comes to changes in velocity and displacement. So doing it with forces is exactly the same as doing it as a net work problem. It's going to be the same stuff. You're going to do all of the same things. But tracing energy feels easier than having to go through the process of setting up a free body diagram, figuring out what the net force is, finding the acceleration. That's very laborious. This process of using energy is a means of getting to a solution quicker, and it makes some nice assumptions. I don't have to worry about certain parts of the problem. But they're all interrelated. They're all really doing the same thing. So, I started talking about this yesterday, and I have to say, do you remember the questions I asked you guys about calories and all that yesterday? I asked that question to every one of my physics classes, except for E&M, all day long. And nobody in the mechanics classes could answer the questions about it from chemistry. But you guys, first and second period, answered almost every single one of them. So something's wrong there. They didn't know. They didn't know what a calorie was. They didn't have any real way of describing any of the stuff that we had talked about in class. I was very disappointed in them. But anyways, do you remember that it's 4,190 joules for every 1 food calorie? You guys remember that? All right. So I'm sure somebody in the room works out. Let's say you're going to bench press as your means of working out this afternoon. Give me a realistic weight. I know everybody's gonna be nervous about this, but a few of you work out pretty regularly. What would be your bench? It doesn't have to be your max, just something that you could do easily and repetitively and have good form. All right, so let's say 120 pounds. So we're talking about the bar and a couple of plates. So 120 pounds, let's convert this to kilograms. Of course, everything we do in this class is in kilograms. So if you could divide that by 2.2 for me, this will tell me the number of kilograms we're actually going to be lifting. All right, so how about we just round up and say 60 kilograms. We won't go low, we'll just say high, it's 60 kilograms. And it's a little bit more than 120, but it'll be all right. My arms are 70 centimeters long, so if I were to perform a bench press, I would say I'd probably gonna be moving the weight upwards 60 centimeters. That seems realistic, nice shoulder width apart. So we're going to lift up the barbell 0.6 meters. All right. How much work is done lifting the barbell upwards the 0.6 meters? This one's a little bit more challenging question in that you have to figure some things out here. For example, if I want to figure out how much work is done, I am going to need the force times the distance times the angle between the applied force and the displacement. But I've done a bench press or two before. How much force do you have to apply to lift the bar? Do I have to apply less than its weight, more than its weight, or the same as its weight?
More.
Now, ask yourself a realistic question. Do I really want to apply more than its weight? If I apply more than its weight, then it accelerates upwards. My understanding is that good form is a controlled motion upwards, followed by a controlled motion downwards. Well, other order probably. Down first and then up. So I bring it down in a controlled fashion, counting to 2 in my head, pause, and then push it back up, counting to 2 in my head. That's supposed to be the method, or some people use a 3 and 2 motion, but I tend to do 2 and 2. So you're supposed to control the weight. I want it to move at a constant velocity. So yes, I have to push it a little hard at the beginning, but for most of the run, I just need to apply a force that is equivalent to the weight. There are 2 forces acting on the bar. There's the weight acting downwards, mg, 600 newtons. And then there's me pushing upwards on the bar. So this is my applied force on the bar. I don't want to push with more than 600 newtons. If I do, then the bar is accelerating and will be going faster when it reaches the top and might keep going. Might just push it right through the ceiling. That's not really my goal. I would like a controlled push upwards so that I can just stop when it reaches the end of my arms. Seem fair enough? So I do work. The work I do will be equivalent to my force times the displacement times the cosine of the angle. That appears to be 600 newtons times 0.6. And would you agree that I am pushing up and the bar is going up? Does that make reasonable sense? So how much work do I do? Looks like 0.6 times 600, so 360 joules of work. This is the work done by me. Everybody okay so far? Following along? Now, if that was the only work being done, then the bar would have a change in kinetic energy at the end of the run. But there's other work being done, isn't there? Isn't there work being done by gravity? Gravity is also applying a force to the bar the whole time. In fact, gravity is applying a 600 Newton force. It does so over the entire time that I push upwards 0.6 meters. But its force is downwards while I am moving the bar upwards, so that's got to be the cosine of 180 degrees. So while I push the bar upwards, gravity does minus 360 joules of work. This means the net work done is 0, which is what I want. I don't want there to be any energy left in the barbell. If there is, it's still moving. I want it to stop when I reach the end of my press. So I'm actually trying to ensure it does not have any residual kinetic energy at the end. Now, here's the thing. I don't know. Let's find somebody. Ron's back. So, Ron, what are you going to have for lunch today? Probably Jell-O? Oh, that's right. Well, you're not a good example, because most people aren't having Jell-O for lunch. So pick somebody else to tell us what their lunch is going to be today.
Colin's probably going to have a Cuban sandwich.
Are you going to have a Cuban sandwich today? What are you going to have for lunch?
I'm going to have like a turkey sandwich, an apple,
All right, turkey sandwich. So 2 slices of bread, turkey, cheese. Any condiment? Dry? Oh my God, man, come on. Flavor is the spice of life. You gotta, all right, so about 100 calories per slice of bread. Say 100 calories with the turkey and 100 calories with the cheese. We're talking 400 calories for your sandwich. You having an apple? All right. Anything else? Anything to drink?
Water.
Good, good. 0 calories there. Anything else?
Like 2 bags of Doritos.
2 bags of Doritos. That's like, what are they? They're 100-calorie bags, so 200 calories per bag. So we're looking at 660 calories for your lunch. All right. There are 4,190 joules of energy for every single food calorie. So can we multiply those 2 things together? 660 times 4,190? Go ahead, tell me it nice and loud.
2,765,100.
All right, so you have consumed this many joules of available energy at lunch. And every bench press, you give the bar 360 joules of energy. So that means your body lost 360 joules of energy with every press. So if you would like to do bench presses as your means of consuming the calories for lunch, how many bench presses would Colin have to do? Go ahead.
7,682.
That's a lot of reps. So I think we have found that as a means to maybe moderate your weight, bench presses might not be the way to go. Now, not making any of this up, if you've ever been on a treadmill or a stair stepper machine, or if you used any machines that monitor the caloric output of your workout, this is how they calculate it. They do nothing particularly fancy. When it comes to anything that's going to be a mechanical device, unless they are physically attached to your heart rate or they are measuring the amount of oxygen that you exhale, they only do this. So the display on the machine, on a treadmill, exactly this, the amount of force based on the angle and how fast it's going. That's why the calorie count doesn't go up as fast as you might want it to. But this is all there is. So why do we do cardio as a means of moderating weight? Because cardio tends to increase the heart rate, does more physical work all over the body, involves more muscles. You would never use weight training as a means of moderating your weight. So you grow muscle that way. You don't moderate weight that way. Your goal in weight training isn't to lose weight, it's to add weight. So this would be the worst way to try and lose weight. Yes, sir.
So when you're going to the gym, are you trying to lose?
This is how much energy it takes to push the barbell up. But it also takes energy just to hold the barbell in place. But you're not doing physical work on the barbell. So contracting muscles requires energy. So to maintain a plank requires energy, but I can't calculate the physical energy transferred to another object while you are planking because you're not moving. So there's not physical energy being transferred. Now, there's still chemical energy being consumed. That's still happening. So for those of you who do yoga or other things where you are pausing in place with contracted muscles, that still will consume calories. Hell, you guys just sitting in classroom learning consumes calories. So the consumption of calories is different than this. But if you're actually interested in trying to monitor how your body uses calories, then you have to be connected to your respiration. So people who are really involved in athletics, they get on a treadmill with a huge face mask, and they measure the amount of oxygen going in and the amount of CO2 coming out. And they try to measure the O2 consumption rate. That's how you actually measure how you are consuming and using calories. There's no other real way to do it. So the human body's complicated. We can talk about physical work. Those are all true things. And the machines you tend to wear to tell you your calorie output, there are varying levels of truthfulness to them. So, unfortunately, any conversation about working out will always make people devolve into side conversations. But if you're very interested in working out, everything I just said was kind of a lie.
Oh,
A lie is the wrong word. Let's do another example because I want to keep moving on with examples. And I know I have limited time, so I'll probably only have a chance to set this example up. But it's okay. This is where we're going to go next. We talked about springs a couple days ago, and I just really mentioned that there's forces from springs. The real usefulness in talking about springs is that it takes work to compress a spring. I want you to remember that if you try to compress a spring, the amount of force necessary to compress a spring is proportional to how much the spring compresses. Hooke's law. We talked about it only one day, and I haven't tested you on it because I knew it would come back today. Now, what that actually means is if I want to pull this box back against the spring and compress the spring, I have to apply a force to the box in order to compress the spring. Well, that's doing work. If I use a force to compress the spring, I have to do work. The problem is that the force changes the more that I compress the spring. So without calculus, I really can't tell you how much work is done, except to give you a formula for the work done on a spring. And the work done on a spring is 1/2 kx squared. X is how much you compress the spring in meters. K is the spring constant. But the thing is, when you do work on the spring, the energy stays in the spring, which means the spring can then release and do work on the box. So we'll talk about that tomorrow. Pick up. So can't go into where this comes from because it involves a little bit of calculus and it's outside the scope of our class. A spring does not provide a uniform force, though. And this is something that I need you to kind of pay specific attention to. This is kind of different than the things we've talked about so far this year, but it's in line with something we did way back in September. If we think about a spring for just a minute, a spring provides a linear force, which means the more you push on the spring, the more force it requires to continue to push it. That's what this states. And we talked about this a long while ago, but it's an unusual force in the fact that we've seen other forces so far this year, but they've all been constant, like your weight is constant. It doesn't change as you move. But for a spring, the more you push in on the spring, the more the force that's required to continue to push on the spring increases. So it's a little bit unusual. What will freak most students out, though, the first time they see it, is something like this. If I was to graph force versus position for a spring, it would be linear. Because it's proportionality. So if you double the amount of displacement on the spring, it requires twice as much force. The slope of that proportionality would be the spring constant. A higher spring constant takes more force to compress, and lower spring constant is easier to compress. Now, I can't do the calculus to show you where the energy in a spring comes from, but you could figure out where the energy comes from if you had a graph. And I want to remind you of two things that were discussed way back in September, that you can be presented with a graph, and that graph is something you will have to evaluate. And when faced with the graph, it's your responsibility to check both what the graph is telling you and what the slope and area could tell you. So let's try it with this particular graph. If you look closely at this graph, the graph itself is force versus position, and it's linear. So if you see a force versus position graph and it's linear, very likely you're looking at a spring. So you might just want that in your notes. They are going to put this on the multiple choice. I am going to put this on the multiple choice. A force versus position graph is the most likely kind of graph outside of motion equations that they'll use. So being able to read one, kind of part of what we need here. Now, again, when faced with the graph, you're asked to check the slope of that graph and you're asked to check the area. Slope of that graph means taking the two values and seeing if A, the ratio of those two values means anything, or if the units of those two values mean anything. This one might not, but this relationship is on the equation sheet. So the Hooke's law of force is on the equation sheet. They're expecting that you can look it up. If I solve that for K, I get F over X. I know the negative sign isn't there. They're not going to put the negative sign on it. They're going to make it positive because the negative sign is about direction. It tells you that the force from the spring is in the opposite direction than you displace it. But you should recognize then that if you have force versus position and it's linear, the slope is likely the spring constant. The area, on the other hand, is force times displacement, which the units would be newtons times meter. If that doesn't look familiar, it's because we've just introduced it. And that means that you need to be cognizant that this is work. The area under a force versus position graph is how much work was done. I'll say it again. The area under a force versus position graph is how much work was done. They can give you any kind of weird kind of force versus position graph. A spring is easy because it's linear. And because it's, linear, you can kind of just see real quick that the area here is going to be a triangle. Now, you can get the 1/2 kx squared from that triangle if you really, really, really work at it. It's not particularly hard to do, but I don't want to spend a lot of time showing you that it comes from there because it's not worth the effort. I just want you to believe me that if you looked at this area, if you look at this area and you're careful about it, you can produce this function. And you would start by just doing the actual area, which would be, I got an F here and an X here. The area would be 1/2 K times X, not K, F times X. That's where you would start. I guess I'm doing this. So if you go over to here, this point would be equal to Kx, which is why this turns into 1/2 Kx times X. That's where the 1/2 Kx squared comes from. I don't care if you know that. What I do care about is that you know these two important features. That the area under a force versus position graph is the work done. That's the first thing I really want you to know. And the second thing I really want you to know is that if it's linear, it's very likely the graph of a spring. So before I launch into a bunch of questions, this is the most likely way you would see this on a test. they'll present you with a graph like this and say, this is the graph of the net force acting on your object. And your object has that's the worst object ever. Let's try a better object. So your object is some box, and it experiences this net force here. And the box is 5 kilograms. The question they might ask is, what is the velocity of the box after it's moved 9 meters? Now, they're asking you to do something very specific. In the case of this problem, what they're telling you to do is to find the area under this curve, set that equal to the net work done, and then use that to figure out the change in kinetic energy. So a work energy graph usually depicts force versus position. And they want you to deal with the area under the graph. They're going to be tricky. They're not going to make it easy. So one of the things that you have to understand, you have to listen for, is the graph the net force, or is the graph just a force? But most of the time when this is on the exam, or most of the time when this is, everybody's trying to look at the bottom of the board, so I'll try and move stuff to the top. But most of the time what they're actually trying to get you to do is find the area under the curve, so the area under this curve, and then set that area equal to net work, which is equal to the change in kinetic energy. And yeah, they tend to do this on multiple choice questions. I don't really know why, but they really do. Now, I don't really care too much about this. This is not a very important topic. This doesn't have a whole lot of usefulness outside of test purposes. It's not going to help you figure things out about how to make a roller coaster. It's not going to make you better at doing physics. It's one of those things that they want you to be able to do to show that you can read a graph that doesn't have any usefulness outside of a test. But sometimes some of the things I have to tell you are just about tests, whether I like them or not. So for this problem, specifically what they would like you to do is find the area. You could break this up into 3 areas if you want, or treat this like a trapezoid, but you would need to figure out what the area is here. I think that a trapezoid kind of works best for me, so that's what I'm going to do. And I'm going to point out that this base is 4 units long, and this base is 9 units long, and the height is 10. So I know the area of a trapezoid, but you can break it up into a triangle, a rectangle, and another triangle. Get that out of my way so I have room to work. So I'm going to say that the area is equal to 1/2. The sum of the bases is 4 meters plus 9 meters. I'm putting those on there to remind us that the base is the part that's in meters. The height is 10 newtons. So I'm going to get something that's in units of newtons per meter. This is 10 times 13, or 130. And then half of 130 is 65. So this is going to equal 65 Newton meters, which hopefully from yesterday you remember is 65 joules. So if this is the work done by a net force, then that means this is the net work. Now, you guys get stuff wrong in the tests because you don't pay attention to little details. So hear this again. This is the work done by a net force. Therefore, it is the net work. If this was the work done by a force, you couldn't guarantee that this would be equal to the change in kinetic energy. we're going to do an example just like this in a minute. You have to pay attention to those little stupid details. What should become important in your notes right now is the word net. Look for that word. Understand it changes the meaning of the sentence when the word net is there. And be prepared to understand what that means. So they have to tell you that this is the only force acting on the object, or it's the net force acting on the object. Otherwise, you actually can't use it to figure out what the velocity is. But as long as it's the net force acting on the object, you can use it to figure out the velocity. I can't write over there. I'm out of space. There. There. Now, I have no desire to put the 5 over here and actually work this out. I really don't want to do that. I think you guys can plug and chug, but I've put 2 or 3 of these on your homework, so you'll have to practice it. It's going to be on your next test. I'm going to make sure of it. I'm going to make sure I put one of these into multiple choice. It's not going to be an FRQ, but that's where it lives. Does everybody understand? I want to slip it in there because it's related to springs. That's really enough said about this, but I just wanted to make sure I at least brought it up in class once. Now let's talk about using energy a little bit more proactively. First, I need to give you this example. I was a little negligent yesterday. I should have done this first. Do you guys remember the elevator problems we did a while ago? I'm going to do the elevator problem again. We got some people inside an elevator. Whole thing has a mass of let's go with 1,200 kilograms. Mass of the elevator. Right? So there's a tension in the string of 15,000 newtons. And it acts on the elevator over the distance of 3 meters. Okay. I can think of 3 questions related to this problem that at this point you should be able to do. The hardest one by far would be just asking, what is the velocity of the elevator after 3 meters? That gives you the least amount of information about what I would like you to do. The easiest question I can ask you is what work is done by tension? A deceptive question to ask you is what work is done by gravity? And the least obvious one, but the one you could answer right off, is what is the net work done? On the elevator, but I'm out of space. Now, these questions are asked out of order. You can't do question number 1 without either doing Newton's laws or answering questions number 2, 3, and 4. So what I'd really like you to do is do these out of order and do this one first. That one's the easiest question here. Do this one next, because once you understand what's being asked, it's pretty easy. And then I think what you're going to get for answer number 4 is pretty obvious. So try 1 and 2 and see if you can do them on your own. And I think it'll only take you about, quite literally, if you figure out what you have to do, 60 seconds. And then we'll come back together and I'll tell you, what I want you to be able to do with this kind of stuff. So if you don't know what I'm asking you to do, well, you're going to be in a world of hurt. Like somebody who's been gone for like the last week. They have no idea what to do. Glad you're back. You want to move that thing out of your way?
Oh, no, I'm good.
Right. Eye shoes in your way? Connor, you in your way? All right.
Force times displacement times cosine. On this case,
Do you guys know what direction the elevator goes? Good. Do you know what direction the tension pulls? I mean, I drew a freaking picture. I'm hoping that you can figure that one out. What is the angle between up and up? 0 degrees, that's right. I did not ask you to do anything particularly hard. Work is force times displacement times the cosine of the angle. So if we consider what we have here for a picture, tension is pulling with 15,000 newtons. The elevator moves 3 meters. And the angle between the tension and the direction it moves is 0. That's it. It was 45,000 joules of energy. It was the work done on the elevator by the tension. That's it. You do have to figure out the weight, which I don't think I'm asking very much. If it's 1,200 kilograms, the weight is 12,000 newtons. So let's talk about that force. That force is 12,000 newtons. How far does the elevator go?
3 up.
Still 3 meters. Does that change?
No.
What is the angle between the direction the elevator moves and the force of gravity?
180.
Negative 36,000. That's it. Now you can just add those together to get the net work. One's positive, one's negative. All you need to do is add them together to get what the total work's going to be. Now, that's just 45 minus 36. So 9,000. Do you understand now why you can do that part first to get what the last question's asking? Because now that you have the net work, this equals the change in kinetic energy. Yes, ma'am?
Why is like the work done by tension like a 0 degree angle and then the work done by gravity 180 degrees?
All right, so this cosine theta is the angle between the displacement of the object and the direction of the force doing the work. So the tension pulls up,
Yeah.
and the elevator goes upwards. So what would the angle be between those two arrows?
0?
It's 0. It's moving in the direction that the force is acting.
Yeah.
Now, what this angle really is supposed to tell you how much of your force is in the direction of motion.
Yeah.
Well, in this case, the tension is 100% in the direction of motion, right? It's causing the elevator to go upwards.
Yeah.
So all of that force is in the direction of motion. That's why the cosine of the 0 degrees gives us 1 for 100%.
Yeah.
Now, the weight acts downwards. It's actually trying to prevent it from going up. So is it helping the elevator go up or hurting it from going up? Hurting it. It's trying to make it not go up. But mathematically, how do we do that? Well, that's negative work.
Yeah.
Well, the cosine turns negative the moment we get past 90 degrees.
Yeah.
So we're actually looking at gravity, which is pulling downwards, but the elevator is going upwards, so the angle is the angle between those two. That's 180 degrees.
Oh, okay.
Does that make sense?
Yeah.
So that's why we use 180 degrees for that one.
Okay, that makes sense.
Is that good? Good so far? All right. Yes, sir?
Would your initial velocity be 0?
That's probably a good assumption, elevator, yeah. I'd be okay with that. I didn't specify. I would probably have to be more particular on a test. How we doing? Is that all right? These are not particularly hard, but there's more. All right, let's try another one, okay? I'm going to intentionally make this one a little bit more difficult. Okay?
Would the initial velocity of that be 0?
That's what I just said, but yes.
Okay.
Yeah, sorry.
Okay.
You would have to be given the initial velocity to find the final velocity.
Okay.
All right, so again, intentionally trying to make this one harder. Now, I have a tendency to use angles that are easy for you guys to compute. So that's why you see me using 30 degrees all the time. I try to make the math the least intrusive part of what we do. And a test, I know that the book will use like 47.6 degrees. I don't know why. I think it's just they're jerks, but understand that it's any angle here. Not every incline is 30 degrees, although I tend to use it all the time. It's just because I know the sine of it's 50. And the cosine, are 0.5, and the cosine's 0.86. It's easy to use. Let's say that this whole ramp, though, is 5 meters high, and I have a 2 kilogram box. I can only think of 2 forces doing work on the box. If there's no friction on the ramp, I can only think of 2 forces acting on the box. Would you agree? So I'd like you to compute the amount of work done by those 2 forces acting on the box. There's the force of gravity, and there's the normal force. I'm writing force of gravity here, not weight, because I don't want you to confuse it with work. But those are the 2 forces. So I'd like you to compute the work done by each. And I understand I've put you in a difficult position. Meaning, I'm not sure if you know what you should do here. I want to see if you can figure it out. I'm not going to give you long, but talk to your shoulder partner. Maybe they know things. I hate that phrase. My God, I hate that phrase terribly. Talk to somebody near you. Talk it out. There's nothing different about this than any other problem we've done with work.
Normal gravity. Then there's the 2 times force of gravity. That's what I'm thinking here at least. But then we have to actually find the gravity, so must be 10. I don't know.
All right. I know I have limited time because of our special lunch today. So I'm gonna push us along a bit. Nothing different from what I said before. Gravity acts this way. Normal force acts this way. But the object goes this way. That's going to be the direction of motion of the object, right? No doubt, it has to go down the ramp. All right, so let's talk about the normal force first. That one's easy, right? I don't even have to know what it is to know it does no work. What is this angle? 90 degrees. It's 90 degrees. I don't have to know how much normal force there is. It can't do work. It doesn't have any part that points in the direction of motion. So the normal force is whatever times 5 times the cosine of 90 degrees, which I know is 0. Okay, move on. What is the angle between the displacement and the force of gravity?
That would be 60.
60, right? It's got to be 60 degrees. So that's the force of gravity, 20 newtons, because it's a 2 kilogram box. Travels 5 meters down the ramp, times the cosine of 60 degrees. Now, did everybody follow that so far? Nothing different than anything we talked about, right? It's that straightforward. You don't have to do anything else. I mean, yes, I had to know that the other angle was 60, not 30. Again, I don't think I'm asking that much for that one, am I? Cosine of 60 is a half, though, right? So this is 100 joules. So the net work is 100. Now, I'm not trying to confuse you. I'm not at all. But you guys, we have done a bunch of this kind of stuff. So let me
50 joules. 100 times cosine of 60 is 50.
You're right, it's 50. I don't know why I said 100. It's 50 joules. Sorry. But let me get to my point, please, before the time runs out. Let's get rid of this arrow here because it's kind of in my way. I want you to think about something. At least I want to see if you can think about something. Do you remember how much of the weight is this direction? What is the component of the weight down the ramp? You're supposed to memorize it. Have you memorized it yet? Because there's two. There's that one and there's this one, right? You should be memorizing those two components. One of them is mg cosine 30. The other one is mg sine 30. If you haven't memorized that yet, do I need to do pop quizzes to see if you can memorize it? Memorize it. Just stop screwing around. Memorize it. Or I will do pop quizzes. I'll do timed multiple choice tests where you have to have that memorized. Just to make sure. That and your stupid motion equations. So I'm saying this because does this component do any work? Can't. It's 90 degrees from the direction of motion. Does this component do work?
Yes.
Yeah, it points right in the direction of motion. Now, this is going to be hard, but follow me on it. The work done by that component has to be mg sine 30 degrees times the 5 meters times the cosine of 0 degrees. This angle is the angle between the force and the displacement, and that's this way. Theta doesn't always mean the same thing every time. There's two different thetas here. One theta is the angle between the force and the displacement, and one theta is the angle of the ramp. Don't get them confused. They're not the same. And since nobody's pencil's wiggling, write that down. You'll screw that up. Theta stands for every angle. That's why when you look on your equation sheet, there's thetas everywhere. How are you going to know what's what? That's your job. That's why the equation sheet is of limited usefulness. The theta for work is the theta between the displacement and the force you're looking at. Now, by the way, you understand that this comes out to be 50 joules too, right? That doesn't matter whether we look at the weight or we look at the component of the weight. The definition of work takes that into account already. Now, you should be able to tell me how fast it's going at the bottom. I'm leaving out that part because that's just plugging into 1/2 mv squared, and I don't really want to do that. But what if there's a spring down here at the bottom designed to catch the box when it makes it down there? And the spring has a spring constant of 1.5 newtons per meter. Okay. Now I'm going to ask a question that is designed to mess you up. Are you ready? Can we agree that the box will slide all the way down, hit the spring, and we'll push on the spring until it gets stopped? And it's going to press in the spring until the box stops. How much work must be done on the spring? If the box is stopped by the spring, how much work must be done on the spring? This question is so easy. You're writing stuff down, and you should write the question down. How much work will be done on the spring to stop the box? Everybody got it written down? Because I'm going to ask the stupidest, simplest question. How much energy does the box have? The box has 50 joules. If I want to stop it, how many joules of energy do I have to take away from the box? So how much work must be done on a spring? It's that easy. The box is going to compress the spring until the spring has done 50 joules of work on the box. That's it. So if I want to know how much the spring is compressed, well, that has to equal 50. That'd be one way to do it. The energy has to go somewhere. Do you remember that phrase I said? You're accounting for all the energy. The box slid down the ramp, 50 joules of energy when it got to the bottom. When it got down there, it still had 50 joules of energy. To stop it, I have to take away 50 joules of energy. The net work formula tells you that. The change in kinetic energy for the box had to be 50 joules to get it to stop. That work done by the spring, that's how much work is done by a spring. That's really what these problems are going to be like. In fact, we're going to put this in a compact method that does it even better than this. One more thing, though, and I know bell's going to ring any second now. How high was the box? What's that? No, because the ramp was 5 meters. So you have to use trig. It's 2.5 meters high. We'll have to do this tomorrow, though.